Whatever is enclosed in the square bracket, it is called as the coordination sphere. Even though the coordination number is same, how two different geometries are there? It is because of the different hybridization. The cation is named first in both positively and negatively charged coordination entities. Whichever is the cationic part, that is the one which has to be named first. So here, which is cationic? The counter ion is cationic. Hello everyone, this is Ambli Unnikrishnan from the Department of Chemistry. So today we are back with session 2 of the chapter Coordination Compounds. So in the last session, we started off with what is coordination compounds, right? And the different classification of inorganic salts, differences between double salt and a complex salt, as well as the definition of terms related to coordination compounds. So few of the terms we have discussed in the last session itself. The continuation of it we are going to do in this session, okay? So in this session, that is the continuation of the other terms. What is coordination sphere? What is coordination polyhedron? We are going to discuss. After that, an important topic, that is oxidation number of central atom. So how to calculate the oxidation number of a central atom in different coordination compound we are going to see. And then the table of common ligands. So there is a whole table that you have to learn. Right? Not all the ligands are necessary, but it is important to have an idea about each of the ligands and whether they are anionic, cationic or neutral, whether it is unidentate or monodentate, or it is bidentate, or it is polydentate, all of that we have to study. Right? And then moving on to the next important part, that is nomenclature of coordination compounds. So if it is an anionic coordination compound, it is different set of rules. If it is cationic, it is different. So all of this we are going to discuss in this session. Right? So to begin with, what is coordination sphere? The central ion and the ligands attached to it are enclosed in square bracket, which is known as coordination sphere. So already as an introduction, we have discussed about this in the first session itself. So for example, K4Fe(CN6). If we are taking this example, whatever is enclosed in the square bracket, it is called as a coordination sphere. So this is not present inside the coordination sphere. It is a part of the coordination compound, but it is not present inside the coordination sphere. So what is this called as? Even we have discussed about this. This is called as the counter ion, right? So whatever is enclosed in the square bracket, it is called as the coordination sphere. For example, in the complex, as you can see here, K4Fe(CN6), the coordination sphere is Fe(CN6) 4 minus, that is the charge on the coordination sphere, and the counter ion is K plus. So how this charge or oxidation number we are determining, we are going to study in the upcoming slides. Now the next one is denticity. So denticity is defined as the number of coordinating atoms present per ligand. Number of coordinating atoms. So how many atoms are present in a ligand through which it is forming a bond with the central metal atom. So that means already we have studied monodentate, bidentate, polydentate. In monodentate, the denticity will be 1 because using only one atom, it is forming a bond with the central metal atom. So I hope denticity is clear for you. Moving on to the next one, that is coordination polyhedron. The spatial arrangement of the ligands which are directly attached to the central atom or ion is called as coordination polyhedron around the central atom or ion. So we have already discussed that there will be a central metal atom. Surrounding it will be ligands. So how these ligands are arranged in space, based on that arrangement is called as coordination polyhedron. Based on how they are arranged, there will be different geometry also. So if the coordination number is 6, okay, the coordination number is 6 means there will be 6 ligands around it, right? Okay, so if the coordination number is 6 here, the L stands for the ligand and M stands for, yes, the central metal atom. And in all these cases, we are considering the L ligand as monodentate. Okay, so this is octahedral. If coordination number is 6, it is always octahedral. If coordination number is 4, there are 2 possibilities. In both these cases, the coordination number will be 4. It can be tetrahedral shape or square planar shape. Okay, so this is the tetrahedral and this is square planar. Right. In both these cases, how this different geometry is coming? Even though the coordination number is same, how 2 different geometries are there? It is because of the different hybridization. Right. And the next one is if coordination number is 5. Again, there can be two possibilities of geometry. One is trigonal bipyramidal and another one is square pyramidal. Okay, so these are the geometries, and together this is called as a coordination polyhedron. So it's basically how the ligands are arranged in the space, okay, around the central metal atom. Now the next important part is oxidation number of central atom. So we are going to discuss how to calculate the oxidation number of different atoms present in different coordination compounds. Okay, so what does the definition say? The oxidation number of central atom in a complex is defined as the charge it would carry if all the ligands are removed along with the electron pairs that are shared with the central atom. So in a coordination compound, there is a central atom as well as ligands are present. So if we are removing all the ligands and the electron pairs, what will be the charge on the central atom? That is called as the oxidation number. Okay, so that is a definition for it. How to calculate, we are going to study now. So for example, oxidation number of copper in CuCN4 3- is +1 and it is written as Cu1. So let's take this example itself in the beginning. CuCN4 3-. So this is the coordination compound which is given to you, right? So as you can see here, there is a charge on the coordination compound also, that is 3-. Right. Now, in the upcoming slides, we are going to study in detail about each ligand, whether it is an anionic ligand, if it is a cationic ligand, or if it is a neutral ligand, right? And if those ligands are monodentate, bidentate, or polydentate. In detail, we are going to study. So as of now, you can see Cn- here, right? Of course, copper is the central metal atom. So we don't know the oxidation number of central metal atom. So that is what we have to calculate. I keep it as X, because I don't know. And Cn is generally Cn-, right? So it is an anionic ligand and it is monodentate also. It is monodentate, we have studied in the previous session itself. So each Cn will carry 1- charge. So how many are there? There are 4. So can we write it as X plus 4 into -1? Right, each Cn will carry 1 negative charge. So how many Cn are there? 4 are there. So 4 into -1 will be equal to the total charge of this coordination sphere is 3-, right? So I write it as -3. So what is if we expand it, 4 into -1 is -4 will be equal to -3. If I take the 4 to other side, it will become -3 plus 4, right? That is +1. So oxidation number is +1. This is how we have to calculate. So this +1, as I got it as +1, how do I represent it? Copper, and in bracket we mention it as Roman letter 1. Okay. So if I get +2 here, I'll put it as Roman letter 2 there. Okay. Now let's move on to this one. CuNH3 4 times H2O Cl2+. Okay, so here also I do not know the oxidation number of cobalt. That is my central metal atom. I do not know the oxidation number. So I keep it as X itself here. Now the next one is ammonia. It is actually called as amine, A-M-M-I-N-E, amine. So in coordination compounds, when we are naming it, there will be different names for the ligands. It will be not the general name that we use generally. Okay, so NH3 is generally ammonia, but in coordination chemistry terms, it is called as amine. Even this we are going to discuss in detail. H2O is water, right? But we do not use water. It is called as aqua here. Cl is chlorine, but name it as chloride in case of coordination chemistry, which we will be studying in detail. So as of now, we don't know the oxidation number of cobalt, which we have to find. So I keep it as X. Ammonia is a neutral ligand, so it doesn't have a charge. Aqua is also a neutral ligand, okay? But Cl, chlorido, it is an anionic ligand. It contributes -1 charge, okay? Only one chlorine atom is there, so -1 charge. So this both will be 0, so I do not have to consider that. Chlorine contributes -1 charge, will be equal to what is the total charge on the coordination sphere? It is +2, right? So X will be, I take the -1 to other side, it will become +2 + 1, that is +3. The charge will be +3. So how do I write the oxidation number of cobalt? It will be copper 3. Okay, in Roman letters I write. Now the another one you can see, CuNH3 4 times Cl2SO4. Okay, so in this, as you can see here, in both these examples we have discussed, there were no counter ions. What was counter ions? Those ions which are present outside the coordination sphere. But in this case, there is a ion which is present outside the coordination sphere. So we do have to consider that also while calculating the oxidation number. So SO4, it is 2 minus. The charge on sulfate is minus 2. Okay, right? So if the sulfate is having minus 2 charge, to neutralize it, the coordination sphere will be having a plus 2 charge, right? If counter ion is having minus 2 charge, the coordination sphere should have the plus 2 charge. That is why you are not able to see any charge here, right? Because this plus 2 and minus 2 will be neutralized. So now I got the charge on the whole coordination sphere. Now again, I'm going to repeat the same steps which we have done before. I don't know the charge on cobalt, so I keep it as X. Now, amine is a neutral ligand. Now, chlorido, we have already discussed each chlorido minus 1 charge. How many are there? 2 are there. So, 2 into minus 1 will be equal to, what is the charge on the coordination sphere? It is minus 2, right? So, X minus 2 is equal to minus 2. X will be equal to minus 2. If I take this minus 2 on the other side, it will become plus 2, which will be 0. So, on the charge on cobalt will be equal to 0. So, this is how we have to calculate. I hope it is clear. So in both these cases, we did not have to calculate the charge on the coordination sphere because it was already given. But in this case, there was a counter ion. So I do have to calculate the charge on the coordination sphere as well. Okay. So now moving on to the next one. There are two different types of complexes, homoleptic complexes and heteroleptic complexes. So complexes in metal is bound to only one kind of ligand or donor groups. Example, CONH3 6 times 3 plus are known as homoleptic. So homoleptic complexes means whatever ligands are present inside that coordination compound will be the same. Okay. So as you can see, there are 6 ligands, but all of them are amine itself. So they are called as homoleptic complexes. Now moving on to heteroleptic complexes, in which a metal is bound to more than one kind of donor groups. See, as you can see here, CONH3 4 times Cl2. Yes, so there are 4 ligands of amine and 2 ligands of chlorido. So in this case, we can see there are 2 different types of ligands. So it is of course a heteroleptic complex. So if all the ligands are same, it is homoleptic, right? And if it is different, it is heteroleptic complexes. So I hope that is clear. Now moving on to the table of common ligands, which is very, very important. So from this table, which we are going to discuss now, we will be easily able to calculate the oxidation number, as well as it is very important for the IUPAC nomenclature of coordination compounds, right? So let us see. So the first one we are going to discuss is monodentate ligands. Okay, so first we are going to see which all are the monodentate ligands, right? And what is the charge on these monodentate ligands also. So first we are going to study about monodentate ligands which are neutral. That means they don't have a charge. They are neutral. Okay, so first it is NH3. As I told you, the nomenclature, while we are going to name these coordination compounds, name that you have to use is not ammonia, it is amine, A-M-M-I-N-E. It's not single M, it is double M, amine. Okay. Next one is H2O. It is aqua. Even H2O is neutral. Okay. So the name we have to use is aqua. The next one is CO, carbonyl. It is also neutral. NO, it is called as nitrosyl. Pyridine, it is called as pyridine. Okay, so I hope till here it is clear. All of these and N3 also, it is called as azido. So till here are monodentate ligands which are, yes, neutral. So all these are very commonly asked. Okay, and the last one is pyridine. So all of these examples which we have discussed now belongs to monodentate neutral ligands, right? Now we are going to see monodentate ligands itself which are anionic, minus charge will be there. Okay, so N3 is called as azido. Bromine, it is called as bromido, right? It is not bromine, it is bromido, which carries a negative 1 charge. Now Cl is chlorido, Cn is cyanido. All of this are having minus 1 charge, right? Fluorido, F is fluorido, OH is called as hydroxido, right? And ONO is called as nitrito O and NO2 is called as nitrito N. Now what is the difference here? As we have already discussed here, this is an ambidentate ligand. NO2 minus, SCN minus, all these are ambidentate ligands. Using 2 donor atoms, it can form a bond with the central metal atom. So if it is forming a bond with the oxygen atom, it is called as nitrito O. So this O and N stands for using which atom it is forming the bond. So it is very important to mention this also. Now coming on to NO3, it is called as nitrito, and CH3CO minus, it is called as acetato. SCN is called as thiocyanato. NCS is called as isothiocyanato. So even this is a example of ambidentate ligand. If it is forming a bond with the sulfur, it is called as thiocyanato. With the nitrogen, it is called as isothiocyanato. So till here are the examples of monodentate ligands which are negatively charged. Anionic, right? Now moving on to the cationic monodentate ligands. NO plus is called as nitrosonium, NO2 plus is called as nitronium, NH2, NH3 plus is called as hydrosonium. So till here we have to be very clear. So in here these are important. In here bromido, chlorido, cyanido, fluorido, hydroxido, nitrito O, nitrito N, and your thiocyanato and isothiocyanato are very important. So I hope the monodentate ligands, their charge and the name is clear for you. Now moving on to the bidentate. Okay, bidentate, if it is neutral, okay, you have to, that is bipyridine and En, ethane 1,2-diamine. Ethane 1,2-diamine, which is very important. It is CH2NH2, CH2NH2. This is called as ethane 1,2-diamine, which is generally represented as En. Okay, ethane 1,2-diamine, which is generally represented as En. So what is that you have to remember? It is bidentate. Okay, through two donor atoms it can form the bond. Okay, it is having two donor atoms, it is bidentate, but it is neutral. Okay, so this is very important. Now bidentate can also have a charge -2. If it is CO3 2-, it is called carbonato. O2- oxido, C2O4 2- oxalato, SO4 2- sulfato. Okay, so I hope till here it is clear. So carbonato, oxalato and sulfato are very important. Here also ethane 1,2-diamine is very, very important. Okay, so it won't be represented in this full form. It will be always written as En. So I hope this is clear for you. So using this, we are going to study about the nomenclature also. Okay. Yes, so in detail we are going to study about the nomenclature. So naming of mononuclear coordination compounds. The cation is named first in both positively and negatively charged coordination entities. So we have already discussed there can be coordination sphere which is negatively charged and positively charged based on the counter ion which is present. So even if it is the coordination sphere, even if it is negatively charged or positively charged, whichever the cation is, it can be the counter ion or the coordination sphere which is the positively charged one, that is the cationic one. So whichever is the positively charged, that should be named first. For example, K4FeCN6. If you are going to consider this particular coordination compound, yes, this is the counter ion and this is the coordination sphere, right? So the counter ion potassium is having +1 charge. How many are there? 4 are there, right? So the charge on the potassium is +4. So if on the counter ion is +4, what will be the charge on coordination sphere? It will be -4, right? So from here itself you can tell that the cationic part is the counter ion and your coordination sphere is negative, right? So which one you will name first? It will be the potassium part which you have to name first. So that is about the first rule. The ligands are named in alphabetical order before the name of the central atom or ion. So if you have more than one ligand, let's take the example of amine and aqua. In the same coordination compound, you are having NH3 as well as H2. Then which one would you name first? Whichever comes first in the alphabetical order. So that you have to name first. Clear? Now names of anionic ligands end in O and those of neutral and cationic ligands are the same. Exceptions: aqua, amine, carbonyl, nitrosyl. The next one is to indicate the number of individual ligands, the prefix mono, di, tri, etc. are used. If these prefixes are present in the names of the ligand, then terms bis, tris, tetra, kis, etc. are used. So this means that, for example, if you are having 6 cyano groups here, right? So what we have to write? It is hexacyano, not just cyano. How many ligands are there? Based on that, we have to name accordingly. If it is just 1, we can write it as cyano. If it is 2, you have to write dicyano. Okay, if it is 3, tricyano, hexacyano, like that you have to write. That is what is told there. And then if already prefixes are present in the name, for example, En, we have just discussed now, ethane 1,2-diamine, already there is a di there, right? In that name of the ligand itself, there is a di. So in such cases, instead of using di, we'll use bis. Okay, so I hope that is clear. So for example, NiCl2 PPH3 twice is named as dichlorobis. See, this PPH3 is called as triphenyl phosphine. So already there is a tri inside the name itself. So instead of naming it again as this bi, we are using the word bis there. Okay, fine. Now oxidation state of metal is indicated by a Roman numeral in parenthesis. So even this we have discussed. Once oxidation number we calculate, we have to mention it in brackets in Roman numerals, right? If the complex ion is cation, then the metal is named as the element. Okay, so what does that mean? If your complex ion is cation, then the metal is named as the element. Okay, that means if your coordination sphere is cationic and the metal is of course present inside the coordination sphere, right? So if it is cationic, then whatever is name of the element, you have to mention that name itself. So for example, iron in a complex cation is called as iron and platinum is called as a platinum if it is cationic. So whatever is the name, we use that itself, right? Now moving on to the next one, if the complex ion is anion, then the metal is named as suffix 8 ending. For example, cobalt in a complex anion. See, as you can see now, your complex is, the coordination compound or coordination sphere is negatively charged, -2. So in that case, what do you say? Instead of naming it as cobalt, the metal using it as cobalt, we use cobaltate, right? For some metals, the Latin names are used in the complex. Example, for iron, if it is anionic, we name it as ferrate. So all this might be confusing now. Once we start naming the coordination compounds, it will be clear for you. So the neutral complex molecule is named as the complex cation itself. So now let's take one example and let's start naming them. Then it will be easy. So the first one you can see here, PTNH3 twice ClNO2. Okay. So according to the rules, we have to see now, there is no counter ions here. So what we are going to do, we have to calculate the oxidation number also, which we have already studied. So platinum is of course the central metal atom, which I do not know the oxidation number. So I take it as X. Amine is a neutral atom, so it is 0. Chlorido, it is a -1. Right, and NO2 is called as nitrito N, right? It is forming a bond with nitrogen of the NO2. So that also contributes a -1 charge. Okay, so together if we count, it is X -2, right? -1 plus -1, that is -2 will be equal to, this is a neutral coordination compound, there is no charge, so it will be 0. So X will be equal to +2. So we calculated the oxidation number, which we are going to represent it as the Roman numerals. So let that be. Now let's start naming the coordination compound. So as you can see, there are 3 ligands here. One amine is there, chlorido is there, and nitrito is there. So when more than one ligand is there, we have to name it according to the alphabetical order, right? So here amine will of course come first, then chlorido, then nitrito according to the oxidation number. So once we name all the ligands, then we'll go to the metal atom. So the metal atom will be named in the end. So let's start with the ligand. So as discussed, this will come first in the alphabetical order. So how many are there? 2 amine ligands are there. So we name it as diamine. Okay, so that is the first part. 2 are there, so diamine. Next comes in the alphabetical order chlorine. So it is named as chlorido, right? So diamine chlorido. Now the last one is nitrito, and through which atom it is? Nitrogen atom. So we write it as nitrito N. Right. Now let's move to the metal atom, which is platinum. Okay, so we write it as platinum itself, and what is the oxidation number we calculate? It is 2, which we write it in the bracket in Roman numerals. So I hope it is clear. Moving on to the next one, K3CrC2O4 3. Okay, so in this case there is a counter ion. So of course we have to calculate the oxidation number here. So potassium, each potassium will contribute +1 charge. How many are there? There are 3. Okay, so of course the coordination sphere will get a charge -3. Now let's calculate the oxidation number. For chromium, I don't know, I keep it as X. Now C2O4, it is oxalato. Is it monodentate? No, it is bidentate, right? Oxalato is a bidentate ligand, and how many of it is there? 3 is there. So I put it as 3 into -2, right? 3 into -2. Okay, I hope it is clear. It is a bidentate ligand, so each of it will contribute 2. So how many are there? There are 3. So 3 into 2 we are going to take, which is equal to -3, which is the charge. So X minus 6 will be equal to -3, X will be equal to +3. So this is the charge on the chromium atom. Okay, so I hope it is clear. Now, in this case, as discussed before, whichever is the cationic part, that is the one which has to be named first. So here, which is cationic? The counter ion is cationic. So what is the atom here? It is potassium. So we write that first, potassium. Then we move on to the anionic part. Now, anionic part, again, how we have discussed in the previous example, we are going to write here. So, which is the only ligand here? It is oxalato, right? So, how many are there? 3 are there. So, we write trioxalato. Right? Now the ligand part is done. We come back to the metal atom, which is chromium. So we write it as, do we write it as chromium? No, because it is anionic. If it is neutral or cationic, we can write the exact name. If it is chromium, we write it as chromium. If it is platinum, we write it as platinum. But it is anionic. So we write it as chromate, not chromium, chromate. And the oxidation number, which we have already calculated, which is +3. Now moving on to the next one, COCl2, En2. Cl. Here also counter ion is Cl. So it is contributing -1 charge. So what will be the charge on your coordination sphere? It will be +1. Now let's calculate the oxidation number of cobalt. So we don't know the oxidation number. So I put it as X. Now each chlorido will contribute -1 charge. How many are there? 2 are there. So -2. And what is En? It is ethane 1,2-diamine, which we have already studied. It is a neutral ligand, right? So it does not contribute any charge, which will be equal to +1, right? The total charge is +1. So X -2, I'm going to take it to the other side. So it becomes +3. So this is the charge on the cobalt which is present. So I hope it is clear. Now moving on to the naming of it. As you can see again, which is the cationic part here, it is the coordination sphere. So I use that part first and the counter ion will come in the end. Okay. So again, the ligands should be named first. We have 2 ligands here, chlorido and ethane 1,2-diamine. So which comes, of course, it is a C, right? Which comes first. So we write the chlorido. So it is how many chlorido is there? 2. So it comes dichlorido. And yes, you can see already it is ethane 1,2-diamine. Already a di is present. So which prefix we'll use? It is bis, not di. Okay. So we use bis ethane 1,2-diamine. And what is the central metal atom? It is cobalt. In this case, it is cationic. So we don't have to write cobaltate. It is just cobalt, right? Cobalt. And what is the oxidation number? It is +3. And whichever is the counter ion, we write the name of it. It is as chloride. Okay. So I hope it is clear. Next one, CONH35CO3Cl. So here also the counter ion is chlorine here, which contributes a -1 charge. So this will be +1. Now I don't know the oxidation number of cobalt, X. So amine is a neutral ligand and CO3 contributes -2. So X -2 will be equal to +1, X will be equal to +3. So this will be the oxidation number. So now let's name it. Of course, cation is named first. So now we have to consider. This is carbonato, this is amine. Of course, amine comes first, right? So how many amines are there? 5. So pentamine. Then just 1 carbonato is there. So we write carbonato. Now, what about cobalt? Is it cobalt or cobaltate? It is cobalt only because it is cationic, right? Cobalt and whatever is the oxidation number, which is 3. Then which was the counter ion? Chloride. We write that. Okay. Moving on to the next one. HgCOSCN 4 times. Okay. So it is mercury here. Okay. So mercury contributes +1. And hence the coordination sphere will get -1 charge. So oxidation number of cobalt we don't know, we keep it as X. And thiocyanate contributes -1, right? It is an anionic monodentate ligand. So how many are there? 4 are there. So it will get a charge -4. So X -4 will be equal to -1. So X will be equal to +3, right? Oxidation number will be +3. Now again we have to check whether it is anionic or cationic. Mercury is the cationic one. So we have to name that first. Okay. So we write it as mercury itself. Now moving on to the coordination sphere, it is tetrathiocyanato, right? Tetrathiocyanato and then cobalt, right? Will it be cobalt or cobaltate? It is an anionic one, right? So we name it as cobaltate and the oxidation number. Not cobalt, it is cobaltate. Now moving on to NiCO4, okay? So here carbonyl is a neutral ligand. So if it is neutral, this of course the charge on the nickel will be also 0. So how do you name the coordination compound? It will be tetracarbonyl. What is the name used for CO? It is carbonyl, tetracarbonyl. Then we come back to the central metal atom, which is nickel. Okay, so this is neutral, so we can use the name itself, nickel. And what is the oxidation number? It is 0. Next one is CONH3 thrice, H2O thrice, Cl3. So in this case also, let's see here chlorine 3 are there. So altogether it will contribute minus 3 charge. So here the coordination sphere get plus 3 charge. So cobalt it is X, amine it is neutral, aqua is also neutral. So X will be equal to plus 3 itself, right? Both of these are 0. What is the charge on the coordination sphere? It is 3. So oxidation number is of course plus 3 itself. Now let us name it. Aqua is there, amine is there. So aqua is there and amine is there, which we have to name first. Amine will come first. So triamine, triaqua will come, right? Triamine, triaqua. Then coming on to the cobalt part, it is cationic. So we name it as cobalt itself with the charge on it, and it will end with chloride. Okay, oxidation number has to be specified. The last one is K2ZnOH 4 times. So here potassium, yes, plus 2 will be there. Of course, the coordination sphere will get minus 2 charge, right? Now, the hydroxido is having minus 1 charge. Okay, it is anionic monodentate. Each hydroxido is having minus 4. So, minus 1. So, how many are there? 4 are there. So, zinc, I don't know. I keep it as X. Then, for each hydroxido, it is minus 1, right? So, plus 4 into minus 1 is equal to, what is the total charge? It is minus 2. So, X minus 4 is equal to minus 2. X will be equal to 4 minus 2, which is plus 2, right? So, the charge will be plus 2. On zinc, the oxidation number is plus 2. Okay. So, now again, which is the cationic part? It is potassium. So, we write that first, potassium. Then, how many hydroxido are there? 4 are there. So, tetrahydroxido. Now, again, it is anionic. So, we don't name it as zinc, it is zincate, right? It is zincate and the oxidation number 2. So this is how you have to calculate the oxidation number as well as name the coordination compounds, right? So let's do few more examples here. CrNH3 thrice H2O thrice Cl3. So again, chlorine is the counter ion. So here it contributes minus 3 charge. So the coordination sphere will have charge of plus 3. Okay. So first let us calculate the oxidation number. Okay. So I don't know the oxidation number of chromium. So keep it as X. Amine is neutral. Aqua is also neutral. So what will be, of course, the charge on the chromium? It will be whatever is the charge on the coordination sphere, which is plus 3. So oxidation number is done. Right. Now let us name it. Which is the cationic part? Of course, the coordination sphere is the cationic part. So we name that first. So it is aqua and amine. So of course, amine will come first. So we write triamine. Right. So it is triamine. Then comes triaqua. Triaqua. Then we come back to our central metal atom. So it is cationic. So we name it as chromium itself. If it was anion, we should have named it chromate. Right. So now I just write it as chromium itself. Then what is the oxidation number we just calculated? It is 3. So I write that in Roman numerals in bracket. Then one more thing is left, which is the counter ion. So I write that also, which is chloride. Okay, so I write that also. This is how you have to name it. Moving on to the next one, PTNH35Cl Br3. Okay, so bromine, it is 3. Bromine also we have discussed, that is bromido. It is a negative or anionic ligand. So 3 are there. So this contributes minus 3. So of course the coordination sphere will get a plus 3 charge. Right. Now let's calculate the oxidation number. For platinum it is X. For amine, it is neutral, but chlorido contributes minus 1, right? So, X minus 1 will be equal to, what is the total charge? It is plus 3. So, X will be equal to 3 and this 1 goes there. So, it will be 3 plus 1, which is equal to 4. So, oxidation number of platinum we calculated. Now, again, which one is the cationic part? It is the coordination sphere. So, we again start with that itself. So, what is the name we have to give? There is 2 ligands here, amine and chlorido. So, according to the alphabetical order, amine comes first. How many are there? 5 are there. So, pentamine, and what is there? Chlorido, right? Only one chlorine. So, chlorido. Now, coming back to the central metal atom. As it is cationic, we name it as platinum itself, right? So, I write platinum. And in bracket, I write the oxidation number in Roman letters, which is 4. And what is the counter ion present? It is bromine. So, I write it as bromide. Okay. So, I hope it is clear. So, if it was chlorine, I wrote it as chloride. So, bromine, it will become bromide. Okay. Now, moving on to the next one, K4FeCN6. So, in this case, as you can see, potassium is cationic. Right. So, how many are there? 4 are there. So, coordination sphere will get minus 4 charge. Right. So, let's calculate the oxidation number of iron here. It is X. And Cn, it is a anionic ligand. So how many are there? 6 are there. So 6 into minus 1. What is the total charge? It is minus 4. So x minus 6 is equal to minus 4. X is equal to plus 2. Right. So oxidation number is created. Now let's see which one we have to name first. Cationic part we have to name first. So which is the cation here? It is potassium. So I write potassium first. Then I move on to the coordination sphere. So in coordination sphere, I have to name the ligand first. Only one ligand is there. How many are there? 6 is there. And which one it is? Cyano. So I write hexacyano. Right. Now, what do I do with the iron? Should I write it as iron or ferrate? Yes, I should write it as ferrate because it is anionic. So, that also is very, very important. Ferrate. And oxidation number, what it is? Plus 2. I write that plus 2 also here. And counter ion already I have written in the beginning. So this is how we have to name it. So you have to be very careful. If your coordination sphere is negative, the metal should not be named in the same name. If it is iron, it should be named as ferrate. Alright. Now moving on to the next one. Na2NiCl4. So again sodium plus 1 charge will be there. So 2 sodiums are there. So plus 2. Coordination sphere will get a minus 2 charge. Right. So now let's calculate the oxidation number of nickel. For nickel it is X. And for each chlorido, it is minus 1. How many are there? 4 are there. So 4 into minus 1 will be equal to minus 2. The total charge is minus 2, right? So x minus 4 is equal to minus 2. X will be equal to plus 2. So oxidation number done. Now which is the cationic part? It is sodium, right? So I write sodium first. Okay. Now I move on to the coordination sphere. Right. So coordination sphere is the anionic part. So which is the only ligand which is present there? Chlorido. How many are there? 4 are there. So tetrachlorido. Tetrachlorido. Right. And the next one is central metal atom we have to write. So do I write it as nickel or nickelate? It will be nickelate. Right. Yes. Because it is anionic. So we write it as nickelate. And what is the oxidation number? It is 2. So this is how you have to name the coordination compound. So I hope it is clear for you, right? So now moving on to the next one, that is formulas of mononuclear coordination compounds. The following are the rules for writing the formulas. The central atom is listed first. Then the ligands are then listed in the alphabetical order. Polydentate ligands are also listed in the alphabetical order. In the case of abbreviated ligands, the first letter of the abbreviation is used for determining the position of ligands in the alphabetical order. So, as we have discussed before itself, whichever is the ligands, it has to be named according to their alphabetical order, right? Yes, the formula of the entire coordination entity is enclosed in square brackets. Ligand abbreviations are formulas for polyatomic ligands are enclosed in parentheses. Right. Yes. The abbreviations of polydentate ligands. The name will be big. Right. They are mentioned in the abbreviated formed in brackets. Right. Now there should be no space between the ligands and the metal with the coordination sphere. For the charged coordination entity, the charge is indicated outside the square brackets as a right superscript with the number before the sign. Okay. So we have already discussed this. Right. The charge will be present on the top. Right. The charge of the cation is balanced by the charge of the anion. So that we have discussed before itself, K4, Fe, CN6 if we are considering potassium plus 4 charge. So to neutralize it, both of it should be equal, right? So cation if it is plus 4, of course should be minus 4. So this is how you have to calculate. So I hope that is clear, right? Now moving on to the names are given to you. You have to find out the formula for it, okay? So it can be either ways. The name will be given, right? The IUPAC name for the coordination compound will be given. You have to calculate or you have to write the molecular formula for it. Or the formula will be given. You have to write the name. So this part we have already done. From the formula, how to write the name of the coordination compound. Now let's see here. Triamine, aqua, chlorido, cobalt 3 chloride. So from the name itself, there are many things that you have to understand, right? So first there are tetraamine. That means 4 amine groups is there. Ligands are there. 4 amine ligands are there. Aqua, only 1 aqua is there. Chlorido, only 1 chlorido is there. And it is written cobalt 3 chloride. So it is written in the form cobalt itself. So if it is written as cobalt itself means your coordination sphere is cationic, right? And chloride is written in the end. That means chloride is the counter ion, right? So let us try writing that. So as you can of course see, the central metal atom is cobalt. So you write the coordination sphere, inside the coordination sphere cobalt, and tetraamine. So 4 ligands of amine, 1 aqua, 1 chlorido, and counter ion will be chloride. Counter ion will be chloride. So then the oxidation number is given here. So if it is given, how do I calculate that? So that will be the molecular formula for tetraamine, aqua, chlorido, cobalt 3 chloride. Okay. So next one, potassium tetrahydroxidozincate. Okay, so it is given potassium first. So of course we know that that is the counter ion, right? So I write it as potassium first. I don't know how many atoms of potassium is there. I keep it as potassium itself. Tetrahydroxidozincate. Okay, so zinc is there. Tetrahydroxido is there. 4, right? And the oxidation number on zinc is 2. The oxidation number of zinc is 2. We already is given in the name itself. So how do I know how many atoms of potassium is there is what we are going to see. So the charge on or the oxidation number of zinc is +2, we already know, and for hydroxido it is -1, we know. How many atoms are there? 4 atoms are there. So it is -4. So +2 and -4 will give me -2, right? So if the coordination sphere charge is -2, how many atoms of potassium should be there? It is 2 atoms. So it is K2. So this is how I write the molecular formula. K2 ZnOH 4 times. Clear? Now moving on to the next example, potassium trioxalato-aluminate. Okay. So again I know it is potassium. So I write the potassium. Right. Now trioxalato-aluminate. Aluminate. So of course my coordination sphere is anionic. So square bracket I write the aluminium, which is aluminate, right? And trioxalato, which was oxalato, it is C2O4, right? Oxalato, how many are there? Tri are there. So I write the 3 there. Okay. So again, I have to see how many potassium is there. So we already know the oxidation number of aluminium, which is +3. Oxidation number of aluminium is +3. And oxalato, we know that. So oxalato carries -2 charge, right? It is didentate. Each oxalato carries -2 charge. So totally how many are there? 3 are there. So it is -6. So +3 and -6 will give me -3 charge. So if the coordination sphere is having -3, potassium should have +3, right? So how many atoms of potassium will be there? K3, right? So it is K3Al-C2O4 thrice. I hope it is clear. Now moving on into next one, dichlorido bis ethane 1,2-diamine cobalt 3. So here it is given cobalt. So of course that is the cationic part. Your coordination sphere is the cationic part. So there is no other counter ion mentioned here. So let's see. Cobalt is the central metal ion. So I write it as cobalt. Right. Next, dichlorido bis ethane 1,2-diamine. So I have 2 chlorido ligands, Cl2. And ethane 1,2-diamine, I can write it as En, and it is bis given here. Bis is given here means 2 ethane 1,2-diamine ligands are there. So En twice is there, right? And cobalt 3. So this much is given here. So ethane 1,2-diamine, we already know that it is neutral ligand. So it doesn't contribute any charge. Now what is the charge on the oxidation number on chlorido? 1 chlorido, 1 negative charge. So 2 are there. So it will be -2. So of course what will be the charge on cobalt? So that is the molecular formula for dichlorido bis ethane 1,2-diamine cobalt 3. Moving on to the next one, tetracarbonyl nickel 0. So this we have already discussed before, right? Tetracarbonyl. So tetracarbonyl nickel. It is given nickel. So I write the nickel first. Tetracarbonyl means 4 ligands of CO is there, right? And it is of course the oxidation number is 0 means it is neutral ligand and no other oxidation number or charges are required. Now tetraamine diaqua cobalt 3 chloride, right? So again it is cobalt format means of course it is a cationic part is your coordination sphere, and chlorido comes as the counter ion. So tetraamine. So which is a central metal ion here? It is cobalt. So I write the cobalt first. Okay. Tetraamine is there. Tetraamine. 4 amine is there. And diaqua is there means H2O2. Twice, right? Diaqua cobalt. So this much part is done. Now what is counter ion? It is chlorido. So I'll write the Cl here. Now oxidation number is 3, which is given here. So I need to calculate now how many chlorido atoms are there, right? How many counter ions are there? So amine is neutral. Aqua is also neutral. So if this cobalt is having +3, means your chlorido, how many should be there? Of course, it should be 3, right? So this will have a -3, then only your coordination sphere will get +3 charge. Clear? Now next one is potassium tetracyanonickelate. Okay, so again counter ion is potassium, which is positively charged. So I write the potassium first, K2, right? So that is written. Then nickelate, so it is nickel, and tetracyano, 4 ligands of cyano, right? So how many atoms of potassium, how we can calculate? Nickel is 2 is given, and cyano, it is -1 for each cyano, so -4 is there. So totally the charge on coordination sphere will be -2. So of course, to balance that, 2 plus charge should be there. So 2 atoms of potassium should be here, right? Next one is tris ethane 1,2-diamine chromium thrice chloride. Okay, so here ethane 1,2-diamine is there, so already a di is there, that is why we use tris here. Okay, so 3En will be there, and chromium, so CrEn3. That is clear. So which was the counter ion here? Chloride here. So ethane 1,2-diamine is there, which is neutral. So if the chromium is having +3, means of course to balance that there should be 3 atoms of chlorine. Alright, next one, amine, bromido, chlorido, nitrito and platinate. Okay, so here all of this are having only 1, right? 1 amine is there, 1 bromido, 1 chlorido, 1 nitrito N, and platinate 2. So it is given platinate. So that means of course it is an anionic coordination sphere, right? So platinate is given, we write the platinum here. 1 amine, so amine is written, bromido is written, chlorido is written, and nitrito N. Nitrito N means we write it as NO2. If it was nitrito O, we write it as ONO. So it is nitrito N, so we just mention it as NO2, right? Now the oxidation number on platinum is given +2, right? Amine, it is neutral. Bromine, it is -1. Chlorido, it is -1. Nitrito, it is -1. So together if we calculate 2, -1, -1, -1. So that is 2 minus 3, which will be equal to -1. So that will be the charge on your coordination sphere, right? So next one is dichlorido. So next one is dichlorido bis ethane 1,2-diamine platinum 4 nitrate. Okay, so here it is platinum itself, so it is cationic, right? So which is your counter ion? It is nitrate. So I write the platinum here, right? How many chlorido is there? Di. So it is Cl2. Ethane 1,2-diamine, it is bis, which is given. So 2 is there. And the last one is nitrate, NO3 twice. Okay, which is the counter ion. Okay, so that is how you have to write the molecular formula. Last one is iron 3 hexacyanoferrate twice. Okay, so iron 3 is given, right? So iron is given as iron and the ferrate is given here. So that means this first ion you can see here, that is actually the counter ion, right? So that is shown here Fe. So which is the counter ion, and the ferrate you can see is the central metal atom Fe, and how many are there? Hexacyano. So Cn6 is given here. So this is how you have to calculate. So in both ways the questions can be asked. The molecular formula can be given, you have to name the compound, or the name will be given, you have to write the molecular formula. So I hope it is clear. So in the next session we are going to study about the isomerism in coordination compounds. Isomerism, which is also very important. So I hope the concepts that we have covered in this session is clear for you. So that's all for today. Thank you.